Thank you.
Okay, thank you very much. So I'm talking about, let me, first of all, I would thank the organizers for arranging this smooth, very smooth conference, online conference. Well, I will talk about decoupled quark stars in self-interacting brane-stick gravity. This is one of the modified gravity. And in particular, I'm using the quark star equation state back model to find exact solution in this theory by using a particular technique, so-called decoupled technique. So before going to the technique, I would discuss some composition of this universe. We know that our universe contains 72% dark energy, 23% dark matter, and rest of the constituents contain 4% free hydrogen and helium, 0.5% stars, 0.3% neutrinos, and 0.003% heavy elements. So a few words about stable structures. Stars are the most widely recognized astronomical objects and represent the most fundamental building blocks of galaxies. The age, distribution, and composition of the stars in a galaxy trace the history, dynamics, and evolution of that galaxy. Moreover, stars are responsible for the manufacturing and distribution of heavy elements such as carbon, nitrogen, and oxygen. Consequently, the study of the birth, life, and death of stars is central to the field of astronomy. Well, this is the phase of universe, how universe evolved. The first phase is the region where neostars begin to form a clump of dust. So like so many things in the universe, stars begin very small, mere particles in vast clouds of dust and gas. Far from active stars, these nebula remain cold and monotonous for ages. Then like some sleepy little town in a biker movie, everything stirs up when a newcomer speeds up through. So this is the protostar. Over the course of 1 million years, the clump grows in a small dense body, so-called protostar. This is the main sequence of phase. So a star will enjoy most of its life in the main sequence phase. When the protostar becomes hot enough, its hydrogen atoms begin to fuse, producing helium, and outflow of energy begins to the nuclear reactions. So this is the red giant. A star stays in the main sequence phase depending on its size. At the end of main sequence phase, the star reaches size of 100 to 1000 times the size of the sun. The energy of the star is spread out across a larger area, leading to a cooler star. The temperature change causes stars to shine more towards the red part of the spectrum. It is this that gives a red giant its name. So the fate of star depends upon the mass of the object. Smaller star with a mass around 8 times mass of our sun becomes a white dwarf. The star with at least 8 solar masses will eventually become a supernova. So in supernova, the star's core collapses and then explodes. In just a matter of seconds, the core shrinks from roughly 5,000 miles across to just a dozen, and the temperature spikes 100 billion degrees or more. So these are the kind of compact objects. This is the output of collapse of a star. So we have the result white dwarf or neutron star or black hole, depending upon the collapsing object. This is the summary of the life cycle of a star. We have started from nebula, dust cloud, then globule, protostar, brown dwarf, main sequence star, red giant. And then this is the collapse of the object, and consequently we have white dwarf, black dwarf, supernova, and a neutron star, and finally the black hole, depending on the mass of the object. Quark stars, another compact object. Let's discuss quark star. If the collapsing stellar core at the center of a supernova contains mass between 1.5 and 3 more solar masses, the collapse continues until electrons and protons combine to form neutrons. So this produces a neutron star. Gravitational pull is balanced by neutron degeneracy pressure. Most dense object after the black hole. This is a cubic meter of neutron star that would weigh around 400 billion tons. So in fact, quark star is in between neutron star and black hole. The environment in the core of a neutron star is extreme, that rules of nuclear physics may change, leading to the formation of quark star. So this is the structure of matter. This is atom, which has approximately 10 raised to the minus 8 radius, and this is nucleus, then proton, and which has 10 raised to the minus 13, electron less than 10 raised to the minus 16, and then this is, well, quarks are the building blocks of other particles. These are confined particles. They never found in isolation. The energy spent to separate quarks give rise to new quarks. For example, this diagram shows that inseparability of quarks in spite of spending more energy. Here we are spending some energy, and finally we have new quark stars instead of destroying these. So there are 6 types of quarks known as up, down, strange, sharp, top, and bottom. Up and down quarks have the lowest masses of all quarks, and they are generally stable. Strange, charm, bottom, and top quarks can only be produced in high energy collisions. This is let's discuss some characteristics of quark star. This is a hypothetical compact star. Protons and neutrons deconfine in the core of a neutron star due to high temperature and extreme pressure, leading to birth of quarks. Density is much higher than a neutron star. Masses of quark stars lie between 3 to 5 solar masses. This is the well-known equation of state of the MIT bag model. Here, PR is the radial pressure, rho is the density, and B is the bag constant. Different values of the bag constant represent different scenarios. Now, the range of bag constant for massless dense quarks is 58.9 to 91.5, and for massive, it has a range between 56 to 58. There's a link of quark star to the early universe. The detection of strontium in gravitation 170817 mergers suggest the presence of heavier elements within neutron stars. Thus, coarse neutron stars, neutrons or quark stars are like fossils, which allow us to peek in time to the beginning of everything. Now, a few words about the Brainsstick modified theory. There's a well-known Dirac large number hypothesis. This hypothesis provides relationship between ratios of the size of scales in the universe that are force scales which yield very large dimension of numbers. So this is the relation between inertial forces and overall mass distribution holds. If this condition holds, that Gm over R is proportional to 1. Here G is the gravitational constant, M is the mass, R is the radius. Now, the very well-known Hubble law says that the farther a galaxy is, the faster it recedes from us. So this provides that the universe is expanding. This means mass of the visible universe. This leads to that the gravitational constant is not in fact constant, but varies with respect to time. So applying the Dirac's hypothesis to an expanding universe, we obtain that gravitational constant is not a constant, but varies with time. In 1961, Brands and Dick introduced a scalar tensor theory by representing the reciprocal of varying gravitational constant through a massless scalar field. The scalar field is coupled to matter as well as gravity through a coupling parameter omega Vt. Now we discuss self-interacting Brands-Dick theory. Low values of coupling parameter are used to describe cosmic inflation. However, for weak field situations, the value of the coupling parameter must be greater than 40,000. And deviations from GR are insignificant. So the action of self-interacting Brands-Dick theory is given by this expression. And obviously, G is the determinant of the metric tensor, R is the Ricci scalar, omega V is the potential, this symbol is the scalar field, Lm is the matter Lagrangian. We can easily obtain the field equations by varying this action with respect to the metric tensor, and then the wave equation, and here is the quantity. Now let us discuss some properties of compact objects, which are used to discuss the characteristics of the compact objects. This is the equation of state. First, the relation between state determinants, for example, density, pressure, etc. This characterizes the state of matter under a given set of physical conditions. Then the gravitational redshift. This is given by the mathematical expression here. Z is, which is found to be less than 5.211 in this paper. Here, mu is the compactness factor, whose limit is much be less than 4/9 for the gravitational mass. Stability is an important property of a body that causes it to develop forces that restore the original condition when it is disturbed from a state of equilibrium. Here we can say this is the state of instability and this is the state of stability. Next is the causality condition. This is a condition which is obtained through the speed of sound in a medium, which depends on how quickly vibrational energy can be transferred through the medium. For a stable structure, the speed of sound must be less than the speed of light. Next is the Herrera's cracking approach, which also helps to measure the stability of an object. So cracking appears whenever the radial force directed inward in the inner part of the sphere changes its sign beyond some value of the radial coordinate. Based on the concept of cracking and causality condition, Abreu obtained another condition of stability. Thus, the tangential and radial parts, difference of the tangential and radial speed of sound, its absolute value must lie between 0 and 1. And finally, adiabatic index also helps to measure the stability. A system is stable if it can be described through a stiff equation of state. So adiabatic index measures the stiffness and it is given mathematically in this form. And for the stability condition, it must be 4/3. Now, to find the exact solution, we need junction conditions. These are the conditions which are matched at the boundary. So the matching of internal and external geometries at the boundary of star must be smooth. For this purpose, the following conditions must be satisfied at the hypersurface. This is the continuity of the first fundamental form. This is the continuity of the second fundamental form. Now, there are some conditions which are required for a physical acceptability. First, the metric coefficients must be positive and monotonically increasing. The second, the physical parameters, for example, density, pressure, etc., must be maximum at the center and monotonically decreasing towards the boundary. Third, the radial pressure must be zero at the boundary. Next is the anisotropy must be zero at the center. Following energy conditions must be satisfied, that is weak energy condition, null energy condition, strong energy condition, dominant energy condition. Now we come to the exact solutions, and we are going to use the gravitational decoupling scheme. This is the graphical viewpoint of this scheme, that in fact in this scheme we assume some isotropic solution and we find an isotropic solution. Following steps are used to find the solution. First of all, add a new gravitational source in the original energy momentum tensor. We deform the metric potentials to decouple the field equations into two sets. The first set corresponds to the original source. The second set relates to the new source. We assume if known solution for the first set, find a solution of the second set, combine solutions of both sets to obtain a new solution. So we follow this technique to find solution in this theory. Now there are two types of decoupling. First is minimal geometric deformation, and second is extended geometric deformation. Here we are going to use the first one, the minimal geometric deformation. In this deformation, we deform only the radial metric potential by leaving the temporal component unchanged. This works as long as the interaction between the matter sources is purely gravitational. So for this purpose, we consider a line element which is given in this form. Here, obviously, phi and psi are unknown metric functions. We assume the matrix distribution described in the internal configuration of the spherical structure in this way. Here is the matter source. This is the anisotropy, and this is in fact total energy momentum tensor, including the terms of BD theory. Sorry. We can write the field equations in this form. Here are the components of the energy momentum tensor. This is the wave equation. And this is the potential function which is used in this theory. Okay, we use the MGD technique through the transformation, that we are making changes only in radial coordinate. Obviously, this sigma is the decoupling parameter. If this is zero, then it means we have no decoupling. So first set corresponds to sigma equal to 0 and provides the isotropic configuration in this way, rho, p. And the second set, which contains evolution equations for an isotropic source, is given by these expressions. Now we can use the conservation of isotropic matrix distribution, and this is given by this expression. Obviously, effective means including all the terms, whereas the divergence of the additional source leads to this equation. Here are the terms which are used in the previous equation. Okay, we assume in this scheme, we first assume an isotropic solution. So we extend two isotropic solutions to an isotropic domain. First, we assume Tolman 5 solution. This is given by this expression, where omega is here. Okay, we also use another well-known condition, so-called embedding class this is defined as an n-dimensional Riemannian space, which is said to be a class M if n plus m is the lowest dimension of the flat space in which the given can be embedded. We shall also use the Carmarker condition. This is the spherical line element which can be embedded into a 5-dimensional space-time if it satisfies a Carmarker condition in terms of curvature components given by this expression. Obviously, here R2, 3, 2, 3 is not 0. So in the second solution, we assume solution with the Carmarker condition. And in this condition, obviously, we take one of the metric coefficients given in this paper as lambda. And we calculate the temporal metric component in terms of here I, where Q and Q2 are given here. So we shall use these two known solutions to find an isotropic, corresponding anisotropic solutions through this decoupling technique. We have only one unknown remains to be determined the set related to the addition source. For this purpose, we use MIT bag model to determine the unknown deformation function. So first, the anisotropic solution 1. So we use values of constants in solution 1, and the constants in solution 1 are evaluated through matching with Schwarzschild space-time. So we in fact use the junction conditions and calculate the following constants. Now, applying the MIT bagel on stat parameters of solution first, and we obtain this condition where xi1, xi2, xi3 are given here. Unfortunately, we cannot have the analytic part of this solution. We check its behavior graphically. For that purpose, we use the numeric values of mass and bag constant and decoupling parameter for particular radii of stars, which are PSR, HER, and FU. So using these parametric values for 3 stars, we obtain values of different parameters, mass, radius, equation state parameter, then omega nu c are 2 different values of coupling parameter for different stars. So we use these values to draw the graph and check the behavior of the solution. In the first figure, we see that the plots of temporal and radial metric coefficients of the new solution, so-called anisotropic Tolman 5 solution for sigma equal to 0.2. And we can find that these provide the required behavior, that these are positively increasing. Similarly, if we change the parametric value just sigma equal to 0.9, we can have the similar behavior, acceptable physical behavior. Next, we have drawn the graphs of matter variables. Density, pressure, and an isotopic parameter for this solution. And we see that density is positive and it provides decreasing behavior. Similarly, the radial and tangential pressure. And we see that an isotropic parameter is 0 at the center. These all provide the required behavior for sigma equal to 0.2 and sigma equal to 0.9. And next we check the energy conditions for this solution, and we see from figure 5, 6 that a dominant energy condition is satisfied again for the two different values of sigma. And finally, we check the some particular parametric, for example, bias, compactness parameter, and redshift parameter, and they all lie within the limits, within the required limits for the two values of sigma. And finally, we check the stability of this solution. We can see that the graphs indicate that this value of this absolute value lie between 0 and 1 in this graph. And this is the graph of adiabatic index, which indicates that its value is in the required limit. This is the graphical view of sigma equal to 0.9. So we can say that the solution 1 is physical viable as well as stable. Similarly, we can discuss an isotropic solution 2. Values of constants can be found through the matching conditions. Now we apply the MIT bag model to solution 2, and we have this condition here. Sigma 4, 5 are given here. And again, we can check the graphical analysis of this solution by taking these values of mass, bag constant, decoupling parameter, again for the 3 stars. This is the table which indicates the different values of the parameters for 3 different stars. And again, we can draw the graphs for the second solution, and we see that the metric coefficients are metric potentials. They are positive as well as increasing for both values of sigma 0.2 and 0.9. Again, here we see that the density and pressure, they are positive and provide decreasing behavior. Similarly, we can see that an isotropic parameter is 0 at the center. So these are all provide required behavior of the matter variables. And these graphs indicate the behavior of energy conditions which are satisfied. So it means this solution is also viable. And these are the graphs of compactness parameter and redshift parameter, which lie within the limits. Again, for 2 decoupling parameters, for 2 coupling parameters, 0.2 and 0.9. And this is the final graph, which indicates that the value of this absolute tangential and pressure velocity of sound lies within the limits. And again, we see that this adiabatic index is also less than 4.3. So this means we can say that the second solution is viable as well as stable. Okay, I can conclude my talk. We have in fact formulated an isotropic solutions by considering metric coefficients of 2 isotropic solutions. First is the Tarman 4, and through MGD technique in self-interacting transitive gravity. So we have used Tarman 4 solution as well as some other parameters like Karl-Markov condition. The set related to theta has been solved by using the MIT bag model to construct an isotropic quark star models. The graphical analysis of physical attributes indicates that energy density and pressure decrease towards the boundary for both models. This is the graphical comparison by table for the solution 1. We see that for 3 different stars, when we take the coupling parameters sigma equal to 0.2, and isotropy in the first 2 cases, but in the last case, it is positive. Energy conditions are satisfied. Compactness and redshift parameters lie in the required limits, and they are stable in all the 3 cases. Behavior is for sigma equal to 0.9. And for the second solution, we can see that here it is positive, here it is positive, but here it is negative. Energy conditions are satisfied. Compactness and redshift parameter obey the required conditions. And here we see that they provide, in most of the cases, stability. So in fact, we can conclude that our constructed both solutions through this technique are physically acceptable as well as stable. Thank you very much.